Welcome! You're listening to the Uncharted Lancaster podcast, where we explore the hidden histories, forgotten places, and long-buried secrets of Lancaster County. Using modern digital storytelling tools, each episode brings a new piece of local lore to life, revealing the strange, the surprising, and the stories history left behind. Let's begin.
I want you to put yourself in a very specific scenario for a second.
Okay, I'm ready.
You are standing on the muddy banks of a river.
Yeah.
And the year is roughly 4000 BCE.
So we are going way, way back.
Exactly, way back. And the water rushing past you is moving incredibly fast. In some spots, it's remarkably shallow, and the riverbed right beneath the surface is just absolutely choked with these jagged, unpredictable rocks.
That sounds like a logistical nightmare.
It really is. Now, here's the problem that you have to solve. You need to cross this river, and you don't just need to get yourself across, right? You need to move hundreds of pounds of cargo.
Like what kind of cargo?
Like heavy, awkward bundles of hides, massive quantities of processed meat, and, your entire family.
Right, so a simple swim isn't going to cut it.
Not at all. And you obviously don't have a bridge. You don't have synthetic waterproof materials. Yeah. And those famous, lightweight, beautifully stitched birch bark canoes that you've seen in literally every movie about early North America.
Oh, yeah, the classic image.
Right. But the second you drop a delicate birch bark hull into this rushing, rocky water, it would just be shredded to ribbons. I mean, the rocks would tear right through the seam.
So it's completely the wrong tool for the job.
Exactly. So looking at the environment, looking at the raw materials you actually have, how do you conquer this river?
Well, it forces a complete rethinking of aquatic engineering, really.
I mean, you have no choice, right?
Yeah, exactly. The solution to that specific environmental hostility is something that it looks deceptively primitive to our modern eyes.
You mean the dugout?
Right. We tend to view it as just a hollowed-out log, but structurally, it is a localized masterpiece of adaptation. I mean, it is a vessel designed not for grace, but for just pure, undeniable durability.
And that is exactly what we're exploring today. We're going on a deep dive into the surprisingly complex, highly engineered world of the dugout canoe.
It's such a fascinating topic.
It really is. We're looking at the lost engineering of the Susquehanna dugouts, and we're relying on a whole stack of archaeological reports, plus some really incredible historical accounts from the Pennsylvania Historical and Museum Commission.
And there was a modern news story, too, right?
Yeah, a great local news story that we'll get into later. But the deeper you go into the mechanics of how these were built and how they were actually used, the more you realize something crazy.
What's that?
Recreating them today has actually forced modern archaeologists to accidentally prove that we've misunderstood this technology for decades.
Which is honestly a beautiful moment in science.
Okay, let's unpack this, because I want to start by looking at that contrast I brought up a second ago, the dugout versus the birch bark canoe.
Right, because I think most of us have a deeply ingrained mental image of Native American watercraft.
Totally. We picture someone gliding silently, effortlessly, nimbly across this pristine, mirror-like lake in a birch bark canoe.
But structurally speaking, these two vessels couldn't be more different. I mean, they operate on entirely different mechanical principles.
How so?
Well, a birch bark canoe is essentially a tension structure. You build a lightweight wooden frame, and you stretch the bark over it, sealing the seams with pitch.
So it's mostly hollow air and a thin skin.
Exactly. It is a marvel of lightweight design, highly functional for deep, calm waters, like the lakes of the far north.
But it's delicate.
Very delicate. It requires a specific environment to survive, and it requires a specific environment to even exist in the first place. You need regions where birch trees grow large enough to yield massive, continuous sheets of bark.
Which brings us directly back to the Susquehanna River in Pennsylvania. The birch bark canoe is fundamentally incompatible with this environment on multiple levels.
Because the trees aren't there.
Right. First, the right kind of birch trees just didn't grow in this region. You literally lack the raw materials. But more importantly, the river itself would destroy a tension-based craft.
The rocks would just punch right through it.
Yeah, instantly. I was thinking about it like this. If a birch bark canoe is a delicate, agile sports car meant for smooth asphalt, the dugout canoe is a heavily armored off-road tank.
Oh, that's a great analogy.
Right. It is built to take a beating.
That analogy holds up mechanically, too. Because a dugout is carved from a single, solid tree trunk. So it is a monocoque structure,
Meaning what exactly?
meaning the exterior skin is the structural frame. It's all one piece. So it is incredibly heavy. It sits lower in the water.
And I imagine it's exhausting to paddle.
Oh, absolutely. It requires an enormous expenditure of human kinetic energy to paddle against a current. And crucially, it is completely unsuitable for overland portaging.
That was the first thing that really struck me when I was looking at the dimensions of these things in the sources.
The weight of them.
Yeah. If you are hauling a 1,000-pound log out of the water, you are fighting a losing battle with gravity. It made me wonder how they traveled long distances.
Like moving from one river system to another.
Exactly. If these boats are too heavy to carry between waterways, how are they moving across the continent?
Well, they weren't using dugouts for cross-country road trips.
What do they do?
For long-distance overland travel, Indigenous peoples relied on an incredibly extensive, well-maintained network of footpaths. The watercraft was hyper-local.
That introduces a really interesting labor paradox, though, doesn't it?
How do you...
Well, you are investing hundreds of hours of intense physical labor to fell a massive old-growth tree and hollow it out. You are creating this incredibly heavy, slow-moving tank.
Right.
If it's so heavy and localized, what is the return on investment? I mean, why not just build rafts?
Because a raft lacks cargo security and maneuverability, whereas a dugout offers unmatched stability and capacity.
So it's about what you're doing in the boat, not how far you're going.
Precisely. Think about the biomechanics of hunting and gathering. Like your analogy, you don't use an armored tank for a cross-country road trip. You use it when you need to move heavy artillery safely.
So dugouts were the heavy-duty pickup trucks of the ancient world.
Yes. If you need to ferry 10 people across a dangerous, fast-moving river, or if you need a stable, rigid platform to stand upright in while throwing a heavy fishing spear, you need mass.
And that makes total sense. If you are hauling 500 pounds of processed deer meat and rawhides, a lightweight frame boat will just capsize or snap.
Exactly. A dugout will not tip easily, and if it slams laterally into a submerged boulder, the 2-inch thick solid wood hull will simply bounce off.
The geographic spread of this concept is what really recontextualizes it for me, though.
It's everywhere.
It is, because reading the local Pennsylvania history, you almost feel like this is a localized adaptation just for the Susquehanna. But when you zoom out, you realize this is one of the most foundational technologies in human history.
It really is.
The sources suggest dugouts are likely the earliest constructed watercraft in the world.
If we connect this to the bigger picture, the timeline forces a massive perspective shift. I mean, we have European examples like the Pessie canoe in the Netherlands, dating back over 9,000 years.
9,000 years. That's wild.
But we can push the theoretical origins back much, much further.
How far back?
Consider human migration patterns. We know human beings reached Australia at least 50,000 years ago.
Oh, well.
And you do not cross the Wallace Line, that's the Deepwater Straits, separating the Asian continental shelf from the Australian one by accident. And you certainly don't do it by swimming.
Right. You need a craft capable of surviving open ocean swells. You need immense structural integrity.
Precisely. And while the earliest wooden boats haven't survived 50,000 years of rot, the deductive conclusion is that massive solid wood dugouts were the vehicles.
They'd be fitted with outriggers for lateral stability.
Exactly. They facilitated the earliest global migrations. It is a fundamental leap in human evolution, right up there with the control of fire.
And focusing just on the United States, the preservation we see is incredible. The oldest dugouts found here date back 6,000 years.
Usually found in bogs, right?
Yeah, they've been pulled out of these anaerobic bogs and lakes in Florida, Louisiana, North Carolina, Kentucky, Ohio, and Pennsylvania.
And the numbers are staggering.
The sheer scale and variety of these fleets, and I mean literal fleets, is wild. Look at Lake Phelps in North Carolina.
Oh, that's a fascinating sight.
In 1985, the water level of the lake dropped significantly due to a severe drought, and archaeologists were able to survey the newly exposed lake bed.
And what did they find?
In a stretch of less than 2 miles, they found 30 dugouts.
Wow. 30 in one spot.
Yes, some of them were up to 37 feet long, carved entirely from bald cypress.
Now, bald cypress is a highly deliberate material choice.
Oh, really? Why is that?
Because cypress wood contains a natural preservative oil called cypressine, which makes it highly resistant to rot and insects.
So they knew exactly what they were doing.
Absolutely. The people building these weren't just grabbing whatever tree was closest to the water. They were selecting for long-term structural resilience in a wet environment.
And the snapshot of daily life preserved there is just Amazing. In one of those Lake Phelps dugouts, they found a broken early woodland clay pot.
Just sitting inside it.
Yeah. Half the pot was resting inside the hull of the canoe, and the other half was lying right next to it in the mud.
That's incredible.
Like a photograph of a bad day. Thousands of years ago, Someone dropped their pot, left the boat, and the lake just swallowed it.
It really humanizes the archaeology.
But if 30 boats in one lake seems like a lot, the finds at Noonan Lake in Florida completely dwarf it.
That's the really massive site.
Yeah. Archaeologists uncovered over 100 log boats in that single lake.
And what makes the Noonan Lake assemblage so critical to our understanding of ancient engineering is the sheer variance in the designs.
They weren't all just the same log shape.
No, not at all. We are looking at a collection dating from the Archaic through the Woodland period, so it's spanning thousands of years. And the engineering isn't static. It adapts.
What kind of adaptations?
You see varying bow and stern shapes. Some are blunt, some are tapering. You see overhanging platforms on the ends. But structurally, the most fascinating feature is that 19 of these Florida dugouts featured low, solid partitions or thwarts.
Wait, left completely intact?
Yes, carved directly out of the main log.
Like leaving a solid block of wood spanning the width of the boat while you hollow out the rest of it.
Exactly.
I was trying to figure out why you would leave those blocks when I read that. The sources suggested they were maybe structural supports to keep the sides from warping inward as the wood dried, or maybe footholds?
Both are likely, but the dimensions of these Florida boats are what really give away their specific function. They were relatively narrow and incredibly shallow.
Which tells us exactly about the biomechanics of how they were propelled, right?
Right.
Exactly. If a boat is narrow and shallow, you are not kneeling inside it with a short paddle. And you certainly aren't taking it into ocean swells.
Right. You're standing upright. You have a long pole, and you are pushing off the shallow, sandy bottom of the lake or the marsh.
So the physical shape of the boat dictates the posture of the human piloting it.
That's such a cool way to look at it. Contrast that with the dugout found in Ohio. That one was made of oak.
Oh, oak is a totally different beast.
It was over 20 feet long, but it was almost 14 inches deep.
Oak is significantly denser and heavier than cypress or pine. So a 14-inch depth combined with the density of oak completely changes the center of gravity.
Exactly. You can't safely stand up in a heavy oak boat with a deep draft without risking a rollover.
It would flip instantly.
Yeah. And the archaeological reports noted that there were highly polished, worn depressions on the interior floor of that Ohio dugout.
From Neil's.
Yes. That polish was left by centuries of paddlers constantly kneeling in the exact same spots. You can literally see the ghost of an ancient person's knees permanently buffed into the oak.
I love that. The wood itself holds the memory of human posture.
It really does. But as big as a 37-foot cypress boat or a deep oak hull is, that is nothing compared to what was happening on the major continental arteries.
Oh, you mean the Mississippi?
Yes. This is where the sheer physics and scale become almost unbelievable.
If we look at the Mississippi River Valley, the size of the watercraft documented completely upends our assumptions about the complexity of ancient indigenous societies.
It's staggering.
In the 16th century, the Spanish explorer Hernando de Soto kept meticulous accounts of his encounters. And he reported seeing dugouts on the Mississippi carrying 75 to 80 warriors.
Plus the paddlers.
Yes. Propelled by 25 paddlers standing on each side.
I really want to linger on the math of this for a second.
Huh?
50 paddlers, 80 warriors, 130 grown men in a single canoe.
It's hard to even picture.
We are talking about a vessel approaching 100 feet in length.
Wow.
That is the size of a modern multi-million-dollar luxury yacht. But it's not made of welded steel or fiberglass, It is carved from a single, unbroken, massive old-growth tree.
And they weren't just crude floating logs either.
No. De Soto noted that these Mississippi Valley dugouts featured constructed decks, structural seats, and sometimes even woven awnings to protect the chiefs from the sun.
Like a floating pavilion.
Yeah. And the hulls were intricately painted or carved with massive designs of snakes and fishes.
The structural engineering required to create a 100-foot dugout is just staggering. Think about the physics of a log that long in the water.
You'd want to bend, right?
Exactly. Wood is flexible. But a vessel carrying the oscillating dynamic weight of 130 moving humans is subjected to immense torsional stress, twisting forces, essentially, as it moves through river currents.
So how did it not just break?
To prevent the log from simply snapping in half under the sheer weight and movement, The builders had to possess a profound, intuitive understanding of buoyancy, displacement, and the tensile strength of specific old-growth timbers.
It also tells you about the environment they were living in. I mean, to build a 100-foot canoe, you first have to find a 100-foot tall, perfectly straight tree with a diameter massive enough to comfortably seat humans side by side.
The ancient forests must have been unfathomably huge.
They had to be.
It implies a landscape of colossal old-growth timber that simply does not exist anymore. But beyond the botany, a 100-foot vessel implies highly complex social structures.
Right, because of the labor.
You are looking at organized labor on a massive scale. The sheer caloric expenditure required to fell a tree of that magnitude using fire and stone, to hollow it out without compromising the hull's integrity, and to physically move a multi-ton object from the forest floor to the riverbank.
It's an industrial operation.
Exactly. It requires a deeply organized hierarchical society capable of sustaining a dedicated workforce. This scale of technology is driven by the needs of large-scale warfare and long-distance, heavy cargo trade networks.
It is literally a 100-foot yacht manufactured with nothing but fire, stone, and human muscle.
It's incredible.
But I want to pivot back to the Northeast, back to the Susquehanna River and the Chesapeake Bay, because the localized ingenuity in this region highlights a brilliant solution to a totally different mechanical problem.
Which problem is that?
It's about storage.
Ah, right. Storage is the absolute Achilles heel of wooden maritime technology.
Let's set the scene for the listener. In the 1600s, early English explorers like John Smith are navigating the Chesapeake Bay, and they are writing accounts back to Europe, and they are completely blown away by the native canoes.
The scale of them.
Yeah. Smith documents seeing these massive dugouts 40 to 50 feet long and 3 to 4 feet deep. He even calculates their capacity, noting they could carry about 1 passenger per foot of length.
So a 50-foot canoe is carrying 50 people across the turbulent waters of the Chesapeake.
Exactly. And Smith specifically notes an encounter where 5 Susquehanna chiefs crossed the bay to meet his ship. But here is the detail that really stands out.
What did they do?
The chiefs arrived at the bay, left their men and their canoes behind at the shoreline, and continue on.
Which presents a fascinating logistical and physical puzzle.
How so?
Well, the Susquehannock's primary settlements were located miles and miles upriver near present-day Washington Borough in Pennsylvania.
Okay.
As we discussed earlier, paddling a heavy dugout downstream with the current of the Susquehanna is manageable, but getting a 40-foot waterlogged solid wood vessel weighing several tons back upriver.
Fighting against the relentless current.
Right, navigating shallow rapids and avoiding those jagged rocks.
It violates the laws of physics and human endurance. I mean, think about the sheer friction, the physical ordeal of portaging, dragging a multi-ton soaking wet log against gravity up a rocky riverbank through dense brush. It's impossible.
It would literally kill the people trying to pull it.
Exactly. So their solution was elegant in its simplicity. They didn't drag the boats back.
He just left them.
The Susquehannock would use the river as a one-way highway down to the bay. When it was time to return home, they just walked the footpaths back upriver, which was exponentially faster and consumed far fewer calories.
That's brilliant.
They kept a massive fleet of dugouts essentially parked at the Chesapeake Bay for whenever they needed them.
But parking a wooden fleet introduces a severe biochemical problem.
I was hoping you'd explain this because the physics of wood are wild.
Wood is hygroscopic. It constantly exchanges moisture with its environment.
Okay.
When a dugout is sitting in the water, the cellular structure of the wood is saturated and swollen, which actually maintains its shape.
So wet wood is happy wood.
Exactly. But the moment you drag that massive dugout out of the water and leave it on a beach, exposed to the ambient air, the wind, and the direct ultraviolet radiation of the sun, the moisture gradient shifts drastically.
It dries out.
Right, but unevenly. The exterior layers of the wood dry out rapidly and shrink, while the dense interior core remains swollen with water.
Oh, that sounds bad.
It's catastrophic. This uneven shrinkage creates immense internal stress, causing the wood to warp, twist, and eventually develop massive structural cracks that render the boat useless.
So you literally cannot leave it on the beach.
No.
So to save their massive, painstakingly carved wooden boats from drying out and destroying themselves, they sank them.
They deliberately flooded the hulls.
I kept rereading this part of the historical accounts because it sounds so counterintuitive. You spend hundreds of hours building a boat whose sole purpose is to float, and your strategy for preserving it is to intentionally sink it to the bottom of the river.
It sounds crazy, but it works.
The sources show archaeological evidence that indigenous peoples would gather heavy river rocks, load them into the hulls of these dugouts, and sink the entire fleet to the bottom of the bay or lake.
It is a profound, intuitive mastery of thermodynamics and material science, particularly when applied during the winter months.
Why winter specifically?
Because by sinking the dugout below the freeze line, they mitigated a whole cascade of environmental threats.
Let's break down those threats because the physics of winter on a river are brutal.
Absolutely. The first threat is surface ice. As the river freezes, expanding sheets of ice can easily crush a wooden hull left at the water's edge.
Just splinter it to pieces.
Right. But by sinking it to the bottom, the boat is suspended in liquid water, which, due to the unique density properties of water, remains at a stable 4 degrees Celsius even when the surface is frozen solid.
Okay, so it avoids the crushing ice.
What else? Second, they avoided the freeze-thaw cycle.
What does that do to wood?
When water inside the cellular structure of wood freezes, it expands by roughly 9%.
Oh, wow.
That expansion acts like microscopic explosives. It literally shatters the cell walls of the timber from the inside out. Repeated freezing and thawing turns solid wood to mush.
That's terrifying for a boat.
But by keeping it submerged below the ice, the wood temperature remains constant, preventing cellular rupture entirely.
And on a purely practical level, it maintains the constant moisture equilibrium you mentioned, so there is no warping or cracking.
Exactly.
Plus, it serves as the ultimate anti-theft device.
Oh, for sure.
If a rival group comes down the river looking to steal your massive transportation assets, they're going to look at an empty beach and assume you took them with you. They have absolutely no idea there's a multi-ton fleet resting silently under 10 feet of water.
You sink it in the late autumn, and in the spring, you simply swim down, heave the ballast rocks over the side, and the natural buoyancy of the wood brings your perfectly preserved, hydraulically stabilized vessel rushing back to the surface.
It's an engineering marvel. And the proof that this technology was vastly superior for this specific shallow river environment comes directly from the European colonists.
They noticed it right away.
Yeah. When the colonists arrived, they brought their own maritime traditions. Advanced, planked wooden boats built with iron nails and complex internal framing. But they took one look at the local rivers and almost immediately abandoned their own ships.
The historical record of this cultural exchange is very telling. We often assume a unidirectional flow of technology where the Europeans introduced the better way, but here, the coastal Native Americans completely ignored the white settlers' planked boats.
Because the European boats were worse for the river.
Exactly. A Carvel-built or clinker-built English boat relies on seams. When an English boat hits a submerged rock, the force of the impact breaks the caulking, pops the iron nails, and the boat rapidly takes on water.
It sinks.
Right. But when a solid 2-inch thick monolithic dugout hits the exact same rock, the impact is dispersed across the entire massive structure. It might scrape, but it won't shatter.
That makes total sense.
Furthermore, a fully crewed dugout canoe, due to its mass and the synchronized power of its paddlers, could easily outrun or outmaneuver an English boat of comparable size.
The dugouts also had a significantly shallower draft. I mean, they didn't have a deep keel jutting down into the water, meaning they could glide right over shallow sandbars and rocky shoals that would instantly ground and destroy the hull of an English boat.
They were just better suited for the environment.
The colonists recognized this aerodynamic and structural superiority immediately. They started manufacturing and using dugouts themselves, continuing the practice well into the 1800s.
There was that ferry operator, right?
Yeah. The accounts mention a man named John Wright, who ran a commercial ferry operation across the Susquehanna. His business model for transporting heavy pioneer wagons across the river wasn't to build a European-style barge.
What did he do?
Instead, he took 2 massive dugout canoes, lashed them securely together side by side to create a wide, incredibly stable catamaran platform, and literally balanced the wooden wagons on top of them.
It is the ultimate validation of Indigenous engineering.
Truly.
It proves that the dugout wasn't just an artifact of a quote-unquote less advanced toolkit. It was an optimal, highly refined solution to the specific fluid dynamics and geological hazards of the local river systems.
Okay, so we've established the scale of these vessels, the complex thermodynamic strategy used to store them, and why they outperformed European designs. But it brings up a glaring mechanical question.
How do you build one?
Exactly. How do you actually manipulate the raw material? You mentioned earlier that putting a 50-foot log on a sawmill in 1250 AD isn't an option. Without chainsaws, without steel felling axes, and without modern industrial mills, how do you cleanly hollow out tons of solid timber?
It's a huge challenge.
To answer that, we have to look at the incredible world of experimental archaeology.
Oh, I love experimental archaeology. It is an absolutely vital epistemological tool. It bridges the gap between theoretical observation and physical reality.
How so?
Well, you can look at a stone tool in a museum display case behind temperature-controlled glass all day long, but you cannot truly understand its function, its limitations, or the biomechanical toll it takes on the human body until you try to recreate the process.
You have to actually swing the tool.
Exactly. You have to feel the weight distribution of the tool, you have to endure the blisters on your hands, and you have to watch how the organic materials react to stress in real time.
And in 2005, the Pennsylvania Historical and Museum Commission, the PHMC, decided to stop theorizing and start building.
It was a huge project.
Their goal was astronomically ambitious.
Yeah.
They were going to build a full-size dugout canoe using entirely ancient tools and techniques, and they were going to do it as a live public exhibit in front of 6,000 visitors over 17 days at Fort Hunter Park.
And to ensure historical accuracy, they didn't just invent a design. They based their blueprints on a specific archaeological artifact.
The mud pond canoe.
Yes, a dugout discovered in 1935 by a group of boys swimming in mud pond in eastern Luzerne County. That original mud pond canoe dates back to approximately 1250 AD, providing them with precise dimensions, wall thickness ratios, and the distinctive blunt-ended hull shape favored in the region.
The first logistical hurdle is the raw material, though. You can't just drive to a lumberyard. They partnered with the staff of Michaud State Forest, who donated a 20-foot-long white pine tree that had naturally blown down during a severe storm. This log was a monster. It was nearly 3 feet in diameter.
And it was wet, too, wasn't it?
Very wet. It had been lying on the damp forest floor for 7 months, meaning the wood was still very green and packed with moisture. So you have a massive wet log and zero access to metal tools.
Good luck.
I kept looking at the dimensions of the mud pond canoe and trying to do the math on how many swings of a stone axe it would take to chop out 3 feet of solid white pine. I realize it is mathematically impossible to do it before the wood literally rots away.
The physical labor would be absurd.
I was completely stumped until I got to the historical accounts they referenced from 1584.
You are referring to the observations recorded by the British explorer Arthur Barlow.
Yes. Barlow watched native peoples building dugouts in what is now coastal North Carolina, and his accounts reveal a process that is almost entirely dependent on thermodynamics. It's not about chopping. It's about controlled burns.
Fire is the primary engine of excavation here. As you deduced, chipping away 3 feet of solid, fibrous white pine with blunt stone adze would take generations, and the sheer impact force would likely split the log, ruining it.
So you burn it.
Fire does the heavy lifting by breaking down the cellular structure of the wood, the lignin, and the cellulose. But it is a highly volatile tool. You don't want to accidentally incinerate the entire log. You want to sculpt it with pinpoint precision.
So the PHMC team begins the process. First, they apply localized fire to the ends of the log to char and bevel the bow and the stern, being hyper-aware not to let the fire burn too deep and compromise the whole thickness.
That's the easy part.
Exactly. The real engineering challenge is hollowing out the long top trench. And the technique they use to control the internal fire is genuinely brilliant.
The clay.
Yes. To protect the upper edges of the boat, the gunnels, which need to remain structurally sound to keep water out, they mixed a thick slurry of wet river clay and packed it densely all along the upper rims.
The white clay functions exactly like an ablative heat shield on a spacecraft re-entering the atmosphere.
Oh, wow, really?
Yes, it relies on the specific heat capacity of water. As the fire rages inside the wooden cavity, the thermal energy is transferred into the clay. The water trapped in the clay absorbs massive amounts of heat as it evaporates into steam, completely protecting the structural integrity of the wooden rim directly underneath it.
It prevents the fire from cresting over the edge and burning down the outside of the hull.
Exactly.
It's a perfect example of granular, highly localized chemical knowledge that easily gets lost to time, but is instantly validated through practice.
It's genius.
So with the clay heat shield in place, they would light a fire running down the entire center length of the 20-foot log and let it burn for 2 to 4 hours every single morning.
And that softens the wood.
The fire carbonizes the wood, turning the hard, fibrous pine into soft, brittle charcoal. Then They extinguish the flames, and the grueling biomechanical nightmare begins. They have to scrape out all that carbonized material.
And it is slower.
The progress is agonizing. They're removing less than 1 inch of material a day.
It requires immense physiological stamina. Imagine the repetitive strain. The human shoulder joint is not designed for hours of downward angled scraping against resistance.
The lactic acid buildup in the muscles would be excruciating.
But the sequential firing process serves a dual purpose. Not only does it physically facilitate the removal of the interior mass, but the final, lingering cycles of heat serve to aggressively bake and harden the remaining interior wood. It effectively fire treats the timber to resist rot.
But once you have the log hollowed out, you face another chemical problem.
What's that?
You can't just put a porous, fire-scraped microscopic sponge of a log into the water. It will absorb water, become waterlogged, and sink. You have to seal the exterior pores.
Right, you need waterproofing.
The archaeologists smoothed the interior by grinding it with pieces of coarse sandstone, sanding down the splinters. But here's where it gets really interesting. The final sealant. They didn't just rub animal fat on it. They concocted a highly specific chemical mixture. Boiling pine tar mixed with hot wood ash.
Okay.
They applied this thick boiling paste to the wood, then abraded it into the grain using fine wood chips, and finally, they hand-rubbed the entire surface using medium coarse sand.
It's essentially ancient fiberglass resin. You have the pine tar, which is highly hydrophobic, repelling water. You add the hot wood ash, which is highly alkaline and acts as a chemical binder and thickener. And finally, the coarse sand acts as a structural aggregate, filling in the microscopic gaps in the wood grain and creating an incredibly durable, hard-wearing, waterproof shell.
That specific combination of materials is knowledge born of deep, generational intimacy with the local biome.
You don't just guess that recipe.
No, definitely not. So after 17 grueling days of burning, scraping, and chemically sealing this 20-foot log, it was time for the maiden voyage. October 10, 2005.
The big day.
4 archaeologists pushed this massive, heavy, handcrafted vessel into the Susquehanna River, aiming to paddle from Fort Hunter down to City Island in Harrisburg. And it was not a leisurely cruise.
Because of the river conditions?
The water level in the river was unusually low that day, exposing all the jagged rocks. It was a brutal trip. 2 of the 4 paddlers actually had to bail out midway through because the displacement of 4 adults made the draft too deep for the shallow rapids.
They hit rocks.
They hit rocks constantly. But what did the physical dynamics of the boat actually teach them?
It tangibly demonstrated exactly why indigenous populations relied on them. The archaeologists reported that, despite the low water, the canoe's lateral stability was unparalleled.
It wouldn't tip.
Right. It completely lacked the agility and quick turning radius of a lighter boat, and getting it moving from a standstill required a massive coordinated spike in physical exertion.
But once it was moving.
Once they achieved momentum, the physical laws of mass times velocity took over. The sheer mass of the solid wood kept the vessel gliding forcefully forward against the current, requiring far less continuous paddling to maintain speed.
It became an unstoppable kinetic force.
Exactly, easily absorbing and deflecting the harsh impacts of the river rocks that would have shattered a lighter frame.
It proved the structural concept flawlessly, but the craziest part of this entire story isn't the boat itself.
What is it?
The real scientific earthquake generated by the 2005 project came from the specific tools they used to scrape out the charcoal. It led to a realization that literally forced archaeologists to rewrite how they interpret museum collections.
This is the moment where experimental archaeology proves its unparalleled worth.
It really is.
It's not just about proving a historical technique works. It is about rigorously testing the underlying assumptions that field researchers make when they excavate and catalog artifacts.
So let's look at the tools. To scrape out the burnt wood, the team used stone adzes. For anyone unfamiliar, an adze is similar to an axe, but the heavy stone blade is mounted horizontally, perpendicular to the handle, much like a garden hoe.
Designed for carving, smoothing, and gouging out wood.
Exactly. The team used greenstone basalt, which is a very dense metamorphic rock. They spent 8 hours just grinding a single piece of basalt against other rocks to achieve a sharp edge.
8 hours for one blade.
But the real engineering nightmare was the hafting, the process of physically attaching the heavy stone blade to a wooden handle.
Oh, the physics of hafting and adze are incredibly unforgiving.
Because of the impact force.
Yes. When you swing a heavy stone blade down into a piece of wood, the kinetic energy transfers directly into the joint where the stone meets the handle. If there is any structural weakness or improper weight distribution, the sheer leverage of the impact will violently snap the joint.
Which is exactly what happened. At first, they attached the heavy basalt to the bottom of a forked branch. They took a swing, the kinetic energy transferred, and the wooden handle immediately shattered.
Back to the drawing board.
So they had to completely re-engineer the physics. They moved the stone to the top of the fork to change the angle of impact. That was better, but the vibration of the strikes kept jarring the stone loose.
So how did they secure it?
Finally, they had to rely on a complex, multi-layered biomechanical binding. They used animal sinew, which has a unique property. When you wrap it wet, it shrinks significantly as it dries, creating a vice-like grip.
That's a great technique.
They wrapped the sinew, covered that with protective rawhide, and glued the entire apparatus together using boiling pine pitch. It was highly technical and incredibly frustrating work just to make one tool.
But it worked.
But they finally got it working, and they started aggressively scraping the charred white pine log. Now this is where the mystery starts. White pine is a notoriously soft wood. Greenstone basalt is an incredibly hard, dense rock. But as the days of scraping went on, the archaeologists noticed something physically impossible happening to their stone tools.
The dense basalt adzes were developing distinct, highly localized wear patterns.
Specifically, they were covered in striations. Deep, microscopic scratches, running vertically, perpendicular to the cutting edge of the blade, tracking the exact motion of pulling the blade through the wood.
Which defies common sense. How can scraping a soft, burnt pine log leave deep gouges in a rock that is vastly harder than the wood itself?
It creates a fascinating forensic puzzle. The wood shouldn't be able to scratch the stone.
So the team had to look at the microscopic biology of the tree itself.
What did they find?
They theorized two possibilities. First, perhaps the crystallized pine pitch inside the wood, hardened by the intense heat of the fire, was acting as a microscopic abrasive.
But there was a better theory, right?
Yes, the more compelling biological theory involves silica phytoliths.
I had to look up what a phytolith was when I read that.
It's incredible plant biology. As trees, particularly pines, grow, their root systems absorb groundwater. That groundwater contains dissolved monosilicic acid from the soil.
Okay.
The tree draws this up and deposits solid microscopic particles of silica directly into its cellular walls. It serves as structural support and a defense mechanism against herbivores.
And what is silica, practically speaking?
Silica is essentially microscopic quartz glass. It ranks much higher on the Mohs scale of hardness than steel.
Oh, wow.
So when the archaeologists were violently dragging the basalt adze through the charred pine, those millions of microscopic glass-like silica phytoliths embedded in the wood were acting like high-grit sandpaper. They were carving deep striations right into the solid stone.
That biological mechanism is amazing. Soft wood armed with microscopic glass. But the mystery gets even deeper when the team cross-referenced their findings with the historical texts.
So Arthur Barlow accounts again?
Yes. When they went back to Barlow's 1584 accounts of the coastal tribes building dugouts, they noticed a glaring omission. Barlow never mentioned stone tools.
Wait, really? What did he mention?
He specifically documented that the native builders removed the carbonized wood using shells, thick oyster shells, hard clam shells, calcium carbonate, completely bypassing stone entirely.
Which triggered a massive reevaluation of the archaeological record.
Exactly. The PHMC team realizes, wait, if the historical accounts say they use shells and our stone adzes are getting shredded by silica, what do the ancient stone adzes in the museum actually look like?
A very good question.
They literally went down into the archives, dug through 4 boxes of uncatalogued tools, and examined roughly 200 ancient stone adzes in the museum's collection.
And the traditional assumption in archaeology has always been, we found a stone adze. This must be a heavy woodworking toolkit used for felling trees and building canoes.
Right. They expected to look at the ancient adzes and find the exact same perpendicular scratch marks they just created on their experimental adze, proving the theory.
But the physical comparison completely collapsed the theory.
Why?
The microscopic wear patterns did not match.
They didn't match at all. The ancient adzes in the museum collection did have deep striations, but they were running in the entirely wrong direction.
The scratches on the ancient tools ran parallel to the blade edge, horizontally, not perpendicularly.
Which tells a completely different biomechanical story.
Scratches running parallel to the blade do not come from chopping downward into a log. They are the unmistakable forensic signature of the tool being rubbed side to side against another, harder stone during the sharpening process.
The wear was from maintenance. not from hollowing out of vast quantities of phytolith-rich pine.
Furthermore, the geographic distribution data supported this new conclusion.
Oh, where they found the tools.
Yes. When they mapped the GPS coordinates of where all these stone adzes had been unearthed across Pennsylvania over the decades, only about half of them were actually found near major navigable streams or rivers.
Where were the rest?
The vast majority were found deep inland, miles away from where a canoe would ever be constructed or used.
So this is the crux of it. Decades of archaeological assumptions. The idea that a stone adze automatically equates to a canoe-building culture were completely upended by this one experiment.
What's fascinating here is that it demands a profound level of epistemological humility from the scientific community.
Yes.
The experiment exposed a massive systemic flaw in how we interpret artifacts.
That's huge.
Because the most vital lesson the PHMC archaeologists learned during those 17 days of brutal labor was that you do not actually need stone tools to manufacture a dugout canoe.
You just need fire and shells.
The heavy stone adze, which, as we discussed, takes 8 hours to grind and days to engineer a functional hafting joint, is a massive overexpenditure of calories and time. It is structural overkill for removing soft carbonized pine.
Fire does the actual cutting.
Fire does the cutting. The thermal breakdown of the cellulose is the primary mechanism. And once the wood is carbonized, a simple, easily discarded oyster shell, or even just a sharply beveled piece of dense hardwood like hickory, is more than sufficient to scrape out the charcoal.
So it's about efficiency.
Yes. What we see here is equifinality. Two entirely different technological pathways can lead to the exact same physical end product.
A culture utilizing intensive, highly engineered stone tool production, and a culture utilizing nothing but controlled fire and discarded marine shells will both produce a perfectly functional, identical dugout canoe.
This realization makes interpreting ancient artifacts incredibly treacherous. You cannot definitively claim that because a culture navigated in dugout canoes, they must have possessed heavy stone adzes.
And conversely, unearthing a beautifully crafted stone adze in an inland forest does not mean a canoe was ever constructed there. It totally shatters the assumption.
Yeah.
It perfectly illustrates how easy it is to project our modern industrial tool-centric mindset onto the deep past.
We love our tools.
We do. We look at a massive problem, a 3-foot thick tree, and our modern brains think big obstacle requires big, heavy, complicated tool. We look for the axe.
But the ancient, highly attuned environmental mindset was vastly more efficient.
Let the chemical reaction of the fire do the heavy labor, and use a piece of biological trash, a seashell, to clean up the mess. It's brilliant.
It really is.
And that realization brings this entire narrative from the 6,000-year-old archaic period to the 16th century Spanish explorers to the 2005 PHMC experiment all the way to the present day.
To the teenager.
Yes, because this fundamental human urge to look at a massive fallen log, apply fire, hollow it out, and trust your life to it on a rushing river, it isn't dead history. The physical and emotional torch has been passed to a new generation, specifically a teenager in Lancaster County, Pennsylvania.
It is a wonderful, highly personal continuation of the technological lineage. We are talking about Noah Platts, a 17-year-old scout who decided to take on this engineering challenge.
This part of the deep dive really resonated with me because it highlights how accessible history can be. Noah didn't have state funding. He hears through the grapevine about some fallen trees on a friend's rural property. He goes to inspect them and finds a massive tulip poplar log.
Tulip poplar is an excellent choice. It grows incredibly tall, perfectly straight, and often lacks twisting grain or dense knots, which are the exact structural specifications required for a stable dugout hull.
So he secures the log, has it transported to the Susquehanna National Heritage Area, and decides at 17 years old to build a watercraft using fire.
Now, how does a modern teenager learn the intricate thermodynamics of ancient boat building?
The exact way any 17-year-old learns anything complex today.
The democratization of knowledge, YouTube and the internet.
Exactly. He watched a detailed video by a bushcraft group called Northmen for inspiration, and amazingly, he found and referenced the exact PowerPoint presentation that the PHMC archaeologists created back in 2005.
That's a great connection.
He took state-funded, rigorous archaeological data, synthesized it with an online video tutorial, and just got to work in the dirt.
He did make one minor modern concession at the very beginning of the process, though.
What was that?
He utilized a modern gasoline chainsaw to cut a 3-inch deep channel along the top spine of the log. This served as an initial fire trough to concentrate the heat. But once that channel was established, he completely abandoned modern combustion engines and reverted directly to the ancient analog methods.
He used the traditional labor-intensive burn-and-chop method.
Lighting the fires inside the trough, monitoring the thermal spread, letting the flames chemically carbonize the cellular structure of the poplar into brittle black charcoal, extinguishing it, and then physically scraping it out with a hand adze.
And the sheer physiological toll this takes on a human body is staggering. Noah meticulously tracked his time. He logged 183 total hours of intense physical labor on this single tree.
Wow, that's dedication.
And 65 of those hours were spent working in complete isolation. He was repeating the exact same biomechanical motions as the 2005 team, removing one shallow, frustrating inch of charred wood at a time.
The muscle fatigue must have been intense.
He noted in interviews that while the curved blade of the steel adze he used was perfectly suited for the angled downward chopping required to clear the bowl of the canoe, the friction constantly dulled the blade, forcing him to stop and meticulously sharpen it.
Just like the ancients.
He said his arms and shoulders would accumulate so much lactic acid and reach such a state of severe muscular fatigue that he could only physically endure swinging the tool for a maximum of 5 hours at a time before his body forced him to stop.
Which creates a profound, unbroken physical connection across millennia.
I hadn't thought about it like that, but you're right.
Think about the biology of that fatigue. The burning sensation in Noah's deltoids and forearms in 2026, or whenever he finally launched it, is the exact same neurological pain signal felt by the PHMC researchers in 2005.
Which is the exact same fatigue felt by a Susquehanna builder in the 1600s.
Which is the exact same muscular exhaustion felt by an archaic period hunter sitting on the banks of a river 6,000 years ago. The tools may shift from shell to stone to steel, but the biology of human muscle tissue, the physics of transferring kinetic energy through a swinging handle, and the stubborn, dense resistance of carbonized wood have not changed one microscopic iota in 6 millennia.
It strips away all the abstraction of history. It reminds you that you don't need a PhD to understand the deep past. You literally just need a fallen log, some fire, a scraping tool, and an absolutely immense, humbling amount of patience.
Noah's ultimate goal was to dig down 13 solid inches into the poplar, waterproof the porous interior using natural pine sap resin, and drag it down to the river to launch it.
And when a local reporter asked him to anticipate how he would feel on launch day, when the hull finally touched the water, his response was incredibly poignant and telling.
What did he say?
He said he would feel relieved, happy, and really scared.
Really scared. I absolutely love that honesty.
Because you've just sacrificed 183 hours of your life burning and carving a massive piece of timber, and now you have to push it into a swift, rocky, unpredictable river, step inside it, and trust your actual life to your own primitive engineering.
That specific cocktail of emotion, that overwhelming mix of pride, physical relief, and sheer visceral terror as the heavy wood displaces the water is completely timeless.
It really is. It is the exact same knot of fear in the stomach that an Indigenous youth must have felt launching their first build.
It's the same anxiety that a man named Gordon Ness felt back in July of 1908 when the local York Dispatch newspaper reported that he and another member of the Riverside Club departed Long Level in a dugout canoe bound for the open waters of the Chesapeake Bay.
It is a shared, hyper-specific human experience that echoes perfectly across deep time.
It perfectly illustrates a foundational truth about human existence. We often obsess over how rapidly our surroundings and our digital technologies evolve. But our fundamental tactile interaction with the raw natural world, our negotiation with the immutable elements of earth, deep water, fire, and dense wood remains a constant grounding force.
The physics of buoyancy do not care what century it is.
Exactly.
So what does this all mean? We started our dive standing on the banks of a hostile, jagged river that flat out rejected the delicate tension engineering of the birch bark canoe.
We discovered that the solution, the dense, heavy monocoque dugout, was not just a local quirk, but an ancient global phenomenon of staggering scale.
Capable of crossing oceans 50,000 years ago and scaling up to 100-foot-long wooden leviathans carrying 130 men on the Mississippi.
We learned the genius thermodynamic strategy of the Susquehanna, intentionally sinking their fleets to manipulate the freeze-thaw cycle and survive the brutal winters.
We saw how experimental archaeologists in 2005 used wet clay as an ablative heat shield to resurrect this lost art, only to have the microscopic silica in the wood accidentally prove that their own museum collections of stone tools had been completely misread, for decades.
And we ended with a 17-year-old kid, his shoulders burning with lactic acid, keeping a 6,000-year-old tradition alive with fire and a tulip warbler log in his backyard. It demonstrates that true, lasting innovation isn't always about creating the most complex, fragile machine possible. Sometimes the peak of engineering is the absolute mastery of something elemental and simple.
The dugout canoe is the ultimate testament to working seamlessly with the hostile physics of your environment, rather than attempting to fight against them. I want to leave you with one final thought to mull over today. Think deeply about that archaeological plot twist we discussed with the greenstone asses.
The scratch marks.
Right. For decades, brilliant scientists looked at the microscopic scratch marks on those ancient stone tools and assumed, with total confidence, that those scratches proved the tools were used to violently chop down trees and build massive wooden canoes.
But a single physical experiment proved that those scratches were simply from the mundane act of sharpening the blade against another rock.
And that you didn't even need stone tools to make the boat in the first place because fire and seashells did the work. They completely, fundamentally misread the wear and tear left behind by a vanished culture.
It makes you wonder.
It really does. So I want you to look around your physical environment right now. Look at the objects you physically interact with every single day. If archaeologists dig up our civilization 6,000 years from now and they don't have our context, what are they going to completely misunderstand?
Oh, that's a great question.
When they look at the microscopic repeated wear patterns on your glass smartphone screen, or the oils worn into the faded keys on your laptop keyboard, or the specific friction wear on the steering wheel of your car, what totally incorrect, wildly imaginative, and deeply logical assumptions will they make about how you actually lived your life?
What if the technologies and objects we think define our entire existence are interpreted by the future as just the crude tools we use to sharpen something else entirely?
Thank you so much for joining us on this deep dive into the river. Keep questioning the assumptions behind what you know. Keep looking closely at the invisible mechanics of the world around you, and we will see you on the next deep dive.
Thanks for listening to this week's episode of the Uncharted Lancaster podcast. If you enjoyed the episode, be sure to subscribe and leave a rating or review wherever you listen. It really helps more people discover the show. For more fascinating local history, visit unchartedlancaster.com. And if you'd like to go deeper, check out one of Adam Zern's books at unchartedlancaster.com/books. Until next time, keep exploring.